Okay, in this video we are going to again determine where the function is increasing, decreasing, and has maximum and minimum values, but this time we have a different kind of a function with a denominator, so some extra things to worry about. All right, so first things first, think about the domain even if it doesn't ask you that. All right, so on one like this where I have a denominator that could be 0, I am going to have some issues with the domain. And so maybe you set that denominator equal to 0 and solve for x in your scratch work, but I am going to instead notice that my denominator factors, and I'm going to rewrite this function with the denominator factored. You don't have to do it that way, but to me that's an easier way to think about values of x that I need to exclude from the domain. Okay, so I don't want to put in any values of x that would make the denominator 0. That's the issue with domain in a fraction when you have a denominator. So maybe when it's factored like this, it's easy to see that if I put in x equals -1, that would make this factor 0. Or if I put in x equals +1, that would make this factor 0. So I need to exclude x equals plus or minus 1. So I want x to not equal plus or minus 1. And so sometimes in algebra, maybe you just wrote something like this for the domain. I'm going to go ahead and write it in intervals since our answers for some of these other things will be intervals, just to make sure that we're clear about how to write that as intervals. So if I think about all real numbers except these two values, kind of again thinking about a number line, we're eventually going to have a number line for a sign chart over here. I would have -1 and 1 on that number line, and then I would have all the space left or right or in between. So left of -1, negative infinity to -1, and then between -1 and 1. So I'm going to put a union symbol. I don't care if you use that, but the online homework will often ask for that. And then right of x equals 1, so 1 to infinity. So that's the domain. There might be some other things from algebra that you perhaps remember about this kind of function. These are called rational functions. And thinking about what the graph looks like, and I'll maybe come back and put some of those here after we do what it's actually asking here. But I don't need all those other things. I do need domain in order to answer what it's asking here. All right, so 3 main steps on a problem like this. First things first, think about the domain. Next, critical values or critical numbers. So those are going to occur where the derivative is equal to 0 or does not exist. So I'm going to find the derivative. I'm going to need quotient rule here. I could find the derivative from this form or this form. I'm going to use the original form. It seems a little bit easier here. So I'm going to need quotient rule. So derivative of the first function, the top function here, will be 2x times the second function, the bottom, minus the first function, top, times the derivative of the second function, derivative of the bottom, is 2x, all over the bottom, or the second function, squared. Okay, so when we first just did derivatives, we just found the derivative and wrote it down and kind of stopped there, because we weren't really going to do anything else with it. But here, I'm going to need to set that derivative equal to 0 and solve for x, and then I'm going to need to test the sign of that derivative at different values of x. So for problems like this, you will want to go ahead and simplify this. And so I just want to highlight some mistakes that students sometimes make. So don't make these. But one mistake is that they see this x squared minus 1 here on the numerator and an x squared minus 1 on the denominator, and they want to cancel those. They don't cancel in this problem, unfortunately, because this x squared minus 1, the quantity squared on the denominator, is the denominator of both of these terms. There's one big term of a bunch of stuff times each other before the minus sign, and then all this stuff times each other after the minus sign. This denominator belongs to both of those. And if I cross it out from something that's going on here, then I have neglected the fact that it is the denominator of this part also. So if there is a common thing that you could factor out of the entire numerator and cancel with a factor in the denominator, you could do that. There is a common thing you might see in the denominator, a 2x, that I could factor all the way out, but I don't have a 2x here in the denominator to cancel with, so I'm not going to do that. So one mistake students make is whenever you use quotient rule, you're always going to have some matching things that are very tempting to cross out, but they don't. So don't do that because of the denominator of the second part. The other thing that sometimes students would see on a problem like this is they'll see a 2x here and a 2x here and a minus sign and just cross those out. There is some cancellation with that, but I actually need to distribute things through and then clean that up a little bit, and I will be able to do some cancellation, but it's not the 2x's that cancel, it's something else. Okay, so what do I want to do instead of making those mistakes? I want to do distributive property here. And then this, after the minus sign, is all just one term. I have an x squared times a 2x, so I can just make that all one term, a 2x cubed. This part in the front, I need to distribute that through. Okay, so, and then maybe you'll see that we can get some cancellation shortly after that. So 2x times x squared will be 2x cubed, and 2x times minus 1 is 2x. And then all of this, so I have x squared times 2x. This isn't multiple terms in here, it's just a single term times a single term. So it's x squared times 2x, the same way this was here. So 2x cubed, and I have that minus sign in front of it. Now maybe you can see that I do have some cancellation. All right, on the denominator, I could expand that out if I want. I could factor some more on the denominator if I want. My goal here is to get some stuff to cancel though. So I'm actually, either of those things isn't going to help me cancel anything. So I'm going to leave this denominator like it is. So some of that is sort of thinking a step or two ahead in terms of what might cancel. And the more problems you do like this, the more you'll be able to do that. So the algebra is messy. It's okay if you struggle with it a little bit at first, but you want to just keep getting better and better as you do more and more problems. Okay, but these two do cancel. So that is what cancels. So these add up to 0. 2x to the third minus 2x to the third adds up to 0. So on the numerator, I'm just left with the negative 2x. Okay, so there's my derivative. Now, why did I find the derivative? It didn't really say derivative in here anywhere, right? This that I had written down from a previous video where we talked about increasing and decreasing. Just as a reminder that visualizing where a function increases, that's about where the slope or derivative is positive. Decreasing would be where the slope or derivative is negative. So ultimately what I want to decide is where that derivative is positive and where it's negative. We start, though, by finding the critical numbers or critical values, and that's where the derivative is not positive and not negative. So 0 or does not exist. So I'll write that over here. Find the critical numbers or values. Different people call them different things. Okay, so that's where the derivative is 0 or does not exist. So I've taken my derivative and I cleaned it up here, so I'm going to use this version. So I'm going to start by setting the derivative equal to 0. All right, so I'll have 0 equals negative 2x over x squared minus 1, the quantity squared. Okay, so algebra at this point. It's different in every problem, right? So if I had a polynomial, we had a polynomial in the last video. Polynomial set equal to 0 when we factored, and that helped. In this case, I might recognize that I have a fraction that's equal to 0. And so kind of a general overall strategy, if you have a fraction that is equal to 0, this is what I do every time I have a problem like that. I noticed that I could multiply through both sides of this equation by something that would clear the fractions. So a common denominator. I only have one denominator here, so the common denominator is just that. But if you had more than one thing in the equation, multiply through by that common denominator, and that will get rid of the fractions. So whether you write this out or not, the step of multiplying both sides of the equation, maybe I'll write that on both sides just to emphasize I'm multiplying both sides of the equation by that x squared minus 1, the quantity squared. The reason I'm doing that is to clear the fractions. You have to multiply every term in the equation by that. Okay, so the convenient thing is that on one side of the equation where I have 0, whatever times 0 is still just 0. So that is simple. And then when I multiply the right side of the equation by that denominator, I have this fraction, and then I'm multiplying by that denominator. Maybe you want to think about that denominator as being over 1. So I have a fraction times another fraction, and so these x squared minus 1, the quantity squareds, cancel. That was my whole goal, was to make them cancel. And so all I'm left with over here on the right side then is negative 2x. Okay, which is much easier to deal with than the equation we had before. So at this point, maybe you can hopefully see how to finish that. This is negative 2 times x, so you're going to divide by negative 2, and so you get x equals 0. Okay, so critical values are values of x where the derivative is 0 or does not exist and are in the domain of the function. So I want to check back here. Is that in the domain? X equals 0. Yes, it's in this interval here. So that is in the domain. That's a critical value. Another possible place where I might have critical values would be when the derivative does not exist. Okay, so thinking about my derivative, over here. This is a place where, by the way, hopefully you're having good habits, as I've been trying to emphasize all semester long about labeling your work. When I just went over here to look for my derivative, I need to be able to find it in my work. So here's my original function. That's not what I want to use. I want to look at my derivative. So I need that labeled so I can find it. Here's the simple version of my derivative. Okay, so I want to think about where that derivative does not exist. So this derivative does not exist when the denominator is 0. So that would happen when x is plus or minus 1. We kind of already thought through that with the original function, but slightly different denominator here, but same values of x that would cause trouble. So the derivative does not exist when x is equal to 1 or x is equal to negative 1. Okay, so those are places where the derivative does not exist. And so a lot of times students will list those as critical values or critical numbers, but they're not actually. This is a little subtle detail. These are places where the derivative does not exist, but the definition of critical values is values that are in the domain. These are not in the domain, so they're not really critical numbers. The derivative doesn't exist there, but these are not really critical numbers or critical values. You always want to be checking back with your domain. Okay, so 3 main steps. Domain, first things first, even if they don't ask you about it, because it's relevant for everything else you do. Critical values, so that means looking at where the derivative is 0 and does not exist. So somewhere you've done some work to find the derivative, so you can set it equal to 0 and think about where it does not exist. And then the third part is to make a sign chart. So I'm kind of running out of space, but I'll just do that in the middle here. All right, I'll do that different color, so maybe it's easier to see. All right, so we're going to do a sign chart. And that's a sign chart for the first derivative. Students get confused about what they're making a sign chart for. It's about the first derivative because we're thinking about where the first derivative is positive or negative. That's where we would have a positive slope or a negative slope, or the function would be increasing and decreasing. Okay, so I'm going to make our sign chart. I want to put on my sign chart any critical values and any endpoints of the domain. So our domain has some endpoints here at -1 and +1. I'm going to put those on here. I'm going to label on this sign chart, though, what is happening at each of those. So at x equals 0, that is a critical value. And the derivative is equal to 0 at that point. I'm going to put up here where I put my signs for my f prime, up here, that f prime is equal to 0 at that point. F prime equals 0 at that point. So visually, you can think about that as a horizontal tangent line. The slope is 0, so flat slope of tangent line. At x equals 1 and x equals -1, just so that when I go to think about what the overall graph looks like, sometimes I'll even put like an open circle here or something, or maybe dashed lines to remind myself that the original function is undefined at those points. So those are a little bit different kind of split points than this one at x equals 0. They do split my region up, but I did some dashed lines there. So this is place where the function is undefined. The original function is undefined. or f of 1 does not exist, we might say, and f of negative 1 does not exist. The function is undefined, then the derivative also does not exist. So if you want to say what's going on with the derivative there, you could say here that the derivative does not exist at that point. Okay. Some of the online homework asks you to fill in what's happening at the points as well as in the regions in between. So just being clear about that. Okay, but what I really want to check here so that I can answer this question about increasing and decreasing is the sign of that first derivative in these regions between. So the critical value and these endpoints of the domain have split the number line into regions. I sometimes call them split points. Our book doesn't use that language, but split points because they split the number line up. So I have 4 regions I need to think about, 4 different regions that I need to think about the sign of the first derivative. And so I can use any of these versions of the first derivative, but this is what I want to use. Again, this is where you want to make sure your work is labeled so that you're looking at the first derivative instead of the original function. Right? So this is what I'm going to test the sign of. Okay, so on this one, I'm going to start with big numbers over here, positive big numbers. So numbers that are bigger than x equals 1. So when I put in a number bigger than x equals 1, like x equals 2 or 100 or whatever, just something bigger than x equals 1, like 2. When I talked about this in the last video, I really just talked about signs, positives and negatives. So if I think about plugging in x equals 2, the numerator, I'll have negative 2 times 2. The numerator will be negative. And then the denominator, notice that because whatever's in here doesn't really matter at this point what is inside there. Whatever's in there is squared. That denominator is not ever going to be negative. No matter what kind of number you end up with in here that you get from plugging in something for x, whatever you get, when you square it, that will make the denominator positive. So that makes this kind of easy, at least in thinking about the denominator when I'm thinking about these signs, because I know that denominator is always going to be positive. So I really just have to think about the sign on the numerator. So when I plug in x equals 2, or something over there, I'll get negative over positive. Negative over positive is negative. So I'm going to put a minus sign here. We could say f prime is less than 0 or negative in that region. Something between 0 and 1. Okay, so pick a number, a decimal, a fraction, whatever, or just think about it. It's still going to be a positive number that you're plugging in. I know that the denominator is going to be positive no matter what I plug in here. And so I just have to think about the numerator. So negative 2 times some positive number in here, that'll be negative over positive is also negative. Right? And then here, between x equals 0 and x equals negative 1, you could pick some decimal or fraction between 0 and negative 1, but really just the sign is all that matters here. So it's going to be a negative number. So you'll have negative 2 times a negative number would make that numerator positive. Denominator is always going to be positive, so positive over positive will be positive. And then over here, left of x equals negative 1, so negative 2 or whatever, but again, the sign is really all that matters. Some negative number that I'm going to plug in. So negative 2 times that negative number will be positive. Denominator will always be positive. Positive over positive is positive. Okay, so I now have done enough work to answer this question. I like to go ahead and draw down here below some arrows to help me think about what's going on with the function. So where the derivative is positive, I have a positive slope. Where the derivative is positive, then the function, I have a positive slope. So positive slope means the function is increasing. And so I sometimes draw these arrows or just write increasing. In this region, between x equals negative 1 and 0, the function is also increasing or going uphill. Between 0 and 1, because the slope is negative, we have a decreasing function. Just visualize what a negative slope looks like. It's going downhill. Negative slope over here also. Okay, so I can now answer intervals where the function is increasing and decreasing. I can also answer about maximum and minimum values. So remember that the function is actually undefined at this x equals plus or minus 1, so there's not a maximum or minimum value there. The only place where there could possibly be a maximum or minimum value is right here. And so if you just think about the functions going up and then back down, then that would be a maximum value. and there is no minimum value on this function. Okay, so I'm going to go ahead and write some answers here for what it asked. We would say that this function, I'm going to abbreviate for some space here. F is increasing on the interval. So we have two intervals here, negative infinity to negative 1, so where x is less than negative 1, and then negative 1 to 0. Cannot really say that whole interval because the function's not even defined right there at x equals negative 1. So even though they're right next to each other, you can't just make that one big interval. So negative infinity to negative 1, and then negative 1 to 0. And f is decreasing on, again, two intervals here. I can't just go through x equals 1 because the function isn't defined there. So 0 to 1 and 1 to infinity. And then I want to give the maximum or minimum value of the function. So we would say here we have a maximum value of the function at x equals 0. And that's the point xy. I'm using this just to distinguish between the intervals that look almost alike. But the point xy, so I've got the x coordinate of the point is 0, and then I'll have to think about what the y coordinate of that point is. And I don't have a minimum value. Okay, so the maximum value at that point xy 0, 0. So I need to find the y coordinate of that point. And so just remembering where you get y coordinates from. Again, that was back in algebra before you knew anything about derivatives, when you got input, output, xy coordinates. So it's not the derivative you're plugging into at this point. It's the original function. So I'm putting in x equals 0 into whichever version of the original function you want. So I get x equals 0, and then I'll get y equals 0 over negative 1, so 0. It's the point 0, 0. Okay, so there might be some other things that you perhaps remember about functions like this from college algebra that could be helpful, or high school algebra or whatever, that could be helpful. This is a rational function, and when you have a rational function like this, you have horizontal and vertical asymptotes. And so the vertical asymptotes are going to occur where the function is undefined at values that are not removable discontinuities, where you could cross out some factors here. So I'll actually have vertical asymptotes. That's why I used dashed lines here, actually. Vertical asymptotes at x equals plus and minus 1. Right, so I'm going to put that up here by the domain. This is just stuff that you would have maybe remembered from algebra. If you don't remember that, that's okay. Vertical asymptotes also at x equals plus or minus 1. Maybe also thinking about a horizontal asymptote, and thinking about that, you might have learned some rules in algebra about degree of numerator and degree of denominator. Horizontal asymptotes are also really about limits. And so you can think about what happens to this function as x grows large, as x approaches infinity or negative infinity. And you could plug in numbers, but I just want to think about it a little bit here. When x is really big, I'll put in a big number and square it on the numerator. And then on the denominator, I'll put in a big number and square it and subtract 1. And so when I'm putting in a really big number for x, that minus 1 has almost no impact. So what happens to the function when x is really big is really controlled by just these two terms, the x squared in the numerator and the x squared on the denominator. And so if I think about x squared over x squared, so as x squared approaches infinity, the y, as x approaches infinity, the y approaches x squared over x squared. It's not equal to that, but it's approaching that because the minus 1 has almost no effect. And x squared over x squared is 1. So I have a horizontal asymptote at y equals 1. And so you can think about the whole graph of this function. We will do some more when we look at second derivative and what it tells you about the graph. But you might be able to get a decent sketch of this function just kind of based on the information we've talked about, even without a graphing calculator. So if I have x and y axes here, I'll have a vertical asymptote at 1 and negative 1, a horizontal asymptote at 1. I have a point at 0, 0. That is a maximum point in that region. I know that between the asymptotes that the function will be increasing and then decreasing. And so it's going to have to go like that. and goes up against those asymptotes. I know on the edges, so right of x equals 1 and left of x equals -1, I know the function is decreasing over here and increasing over there, and I know it's going to have to approach these asymptotes. So you can maybe think about that. If the function's going to be decreasing and has to approach that asymptote, it's going to have to be like that over there. And if the function over here is increasing, read that graph as you go left to right, it's going to go up, but have to approach the asymptotes, so it's going to look like that. So a decent sketch, really, without even needing the calculator. Of course, you can get the calculator to help you refine that a little bit and plot a few more points, but part of the goal of this is to be able to understand the function behavior so that you can be a critical user of what you're seeing on a graphing utility, so that you know if there's any behavior that's hidden or that you need to zoom out or in to see. But based on our work here, this is what we should expect to see when we look at a graphing utility. All right, we'll look at some more examples later when we use the second derivative to determine even more information about these functions.